Good afternoon, everybody. This basically is a continuation of what Alia and Dave has talked about in all kinds of details. So what we want to show here is analyze some of these schemes, actually a subset of these schemes, and look at how they perform in some realistic network scenarios. We specifically consider two types of IP fast readout mechanisms. One is one of the simplest ones, the loop-free alternate, and the second one is what I think Alia pointed out as medium complex, U-turn alternate. The kinds of predictions we look at is a pure link failure. That means we assume that when you detect a local failure, then it is a link failure, and can use our alternate next hop based on that. But we usually cannot distinguish between router and link failure. So if the neighboring router is really the one that failed, then actually we may see some loops. We may not see it in all cases, but at least in some cases. To protect against that, we can do a router plus link failure protection. Basically, we do not use the neighboring router as the next hop. Okay? So that, of course, reduces the number of coverage, but that avoids getting into any possible loop situation when the router actually did fail. In terms of performance measures, the first one that we look at is the coverage or efficiency. Essentially, we just want to say that if there is a failure, if there wasn't any IP fast reroute, then some amount of traffic will be lost for some period of time. We may debate on whether it is 200 milliseconds, 500 milliseconds, or a few seconds. But until the IGP convergence happens, we will have some failures. And how much of the traffic can be saved by doing this IP fast reroute convergence. By the way, the same thing, of course, we could do using MPLS fast reroute, but I am not going to cover that, at least for this talk, since we are only talking about IP fast reroute. In terms of the second point is, in terms of, for a service provider perspective, is that what is the cost of providing this IP fast reroute? For example, somebody could say that, okay, we can provide this great 50 millisecond convergence, but you have to keep 100% more capacity in the network. Then I don't think that most of the service providers will be interested in that. So what we wanted to see is that if we do some of these mechanisms, then how much extra capacity do we need in the network in order to actually make it work? All right, we consider two networks. We name them Network 1 and Network 2. The first one is an IP backbone network with 36 routers and about 49 links. In this case, we have a point-to-point traffic matrix between every pair of routers. And this network and traffic matrix is roughly similar to an existing network. And this is one of the ones we will look at. The second one is what we call Network 2, which is both a combination of backbone and access network. And this is one of the networks, actually, similar to actually one of the networks that we planned for future. In both cases, as I said, that we have a network and traffic matrix. For Network 1, we also wanted to see that if we can tweak the network a little bit, we change the topology a little bit, add some links here and there, and by doing that, if we can improve the convergence. Okay. Now, in terms of what is the meaning of, I guess, coverage, one could define coverage as how many destinations are reachable during this failure condition. That's one way of looking at it. But we really want to look at it from a traffic point of view, because we have seen that there may be some destinations which are not reachable, but they're not carrying any traffic. Whereas there may be a small number of destinations which are not reachable, but they may be carrying a very large amount of traffic. So what we really want to know is, for a given failure scenario, we define X as the amount of traffic that will be lost if we did not do fast reroute. And Y is the amount of traffic that would be lost if we did do fast reroute. That means that is the case where we do not have an feasible alternate next hop. Okay? And the efficiency will be X minus Y, which is the amount of traffic that is lost divided by the total amount of traffic that could potentially be lost, X minus Y over X. That's a simple enough measure. Now, the important thing to note is that this is not uniform. In any given network, we see that there are many links where this number could be 100%, but there could be a few links where this number could be, say, 10% or something pretty small. Okay? So what we will show here is the overall average over the network, and we average over all possible failure scenarios. In one case, all single link failures. In the other case, all single router failures. Okay, these are some initial results. And for Network 1, if we did only loop-free alternate, then we saw that in terms of traffic, the efficiency was about 33%. If we do loop-free and U-turn alternate, that is a big jump. At least in this example, the jump was from 33% to 88%. Now, of course, that is not true for every network. Like just as you see down there for network 2, we did the exact same study. We saw that even with loop-free, we could go to 89%, which probably is quite reasonable already. And if we do, of course, loop-free plus U-turn, there was 100% coverage. By the way, we did see that in this example, there are a few destinations that are not reachable, but those destinations are not carrying any traffic under no failure condition. So we did get 100% coverage, even with the very small destinations not being reachable. Now, another thing that we did is that in network 1, since we knew, as I said, like the good part of the network, coverage was very high. There are some trouble spots in the network where coverage was not getting very well. So we added some strategic links in there, and we saw that there could be a jump. For example, with loop-free, it goes to 43%, and loop-free plus U-turn, it goes to almost 100%, actually 98%. We did actually other studies, for example, as Dave pointed out, that we could solve this problem using network design, and we can. Actually, in this particular network, we did a potential design where we could change things sufficiently so that both kinds of coverage could be close to 100%. So that, again, is something we can have in our back pocket, but from a network provider perspective, what I would like to see is that we don't want to change our network design just to fit in for this IP fast reroute. We would like the algorithms to be fast enough, but of course not too complicated, but algorithms to be smart enough so that whatever topology we give, it should be able to solve that. So from that perspective, I think I can say that only loop-free is simple, it has lots of advantages, but it is not that predictable. That is, if we are lucky, we'll have very good coverage. If we're not lucky, we may not. But if we do, at least in this case, loop-free plus U-turn, or not just U-turn, some of the other algorithms based on tunnel or directed forwarding, they could also give very close to 100% coverage. We don't have to worry about what our topology is. We'll always get that kind of coverage. Okay. Now, that one was a simple picture. We only looked at link failures. Now let's make it more complicated. What happens if we also want to protect against router failures? Okay, that's one thing that we want to show here. The second thing we want to show is that we may not have fast reroute throughout the whole network. We may have only in the backbone. So we show the case where if we have it in backbone only, or if we have both in backbone plus access. And this is the network 2, which was well behaved anyway. So in the link failure case, we get close to 100% in all cases, except that if we did it in the backbone only, and we average over all backbone and access link failures, then it goes down to about 72%. In this case, actually, the backbone router was doing IP fast reroute. So traffic going from backbone to access was mostly being actually saved. Only the traffic coming from the access to the backbone side that was not being saved, and that caused this drop in efficiency. Now, if we go to the last two rows, that's where things are more complicated. That is, we are not going to use a next hop, which is our neighboring router, with the anticipation that the neighboring router may have failed. Okay? So if we do that situation, then even for link failures, our coverage goes down to some extent from 100%. It still stays pretty high, like 86% or 74%, those kinds of things. And for router failure, if we do it in the backbone only, we got 54%. And if we do backbone plus access, we got 64%. So the basic bottom line here is that protecting from router failure is significantly more difficult than protecting against link failure. In fact, we did one more case, which I'm not showing here, that is the SRLG failure. So we looked at a large number of SRLGs in a network similar to an existing network, and there we saw that clearly, just as router failure is more difficult than link failure, SRLG failure protection is also more difficult than link failure, and usually its coverage is less than that of link failure, but we are not showing all the results, at least in this case. Okay, so this is all about coverage. The next item is that how much extra resource do we need? Like, nothing comes for free, okay? What is the price do we have to pay in order to have this great IP fast reroute? In this example, the pink arrow shows the primary path of the traffic before any failure happens, A, B, C, D. Suppose the B to C link fails. So B does a local repair, and it decides that I will go through the path A, B, E, F, D, okay, the top part, all right? And that's fine. After a while, all the nodes have convergence. And if we are lucky, then even after convergence, maybe A will decide, okay, let's use the route A, B, E, F, D, then things will be perfect. Like we don't need any extra bandwidth. The IGP readout and fast readout will be the same. But in many cases, we see that that is not the case. Like IGP readout may take a completely different path because that's based on the global knowledge. It could be going through A, G, H, and D, all right? So in this case, okay, the way we design our network is that we keep enough bandwidth for all primary traffic under no failure. Then we consider all single link failure and all single router failure cases, and in some cases, actually we also do single SRLG failures. We don't show it here. For all single failure cases, we want to make sure there is enough bandwidth for IGP readout only, okay, only the lower part. So now, if we do fast readout, then we also have to make sure that there is enough bandwidth on the top part as well, that is during the fast readout. And the main thing that I want to show is that what is the delta? How much more do we need in order to do fast readout? Okay, this is one example only. In this example, we did actually IGP fast readout only in the backbone. The link utilization limit we had was 85% under normal condition as well as IGP readout, all single link and single router failures scenarios. Now, if we did only IGP readout, we needed in this example network 829 OC48s and about 575,000 OC48 miles. Okay. Now, if we did the same problem with IGP plus fast readout, then this number went up from 829 to 864. This actually is only a 4% increase. So this actually is a positive result that we can get fast readout, but we don't need 50% or 100% more bandwidth. At least in this example, we needed 4% more bandwidth. One more thing to note is that if we looked at the OC48 miles, then the increase was about 7%, which kind of means, at least in this case, when we have to put extra bandwidth, we tend to put it on longer links in order to do this thing. And so the bandwidth miles wide, the increase is somewhat more. But also have to note that in this example, we were doing router failure prevention. So there were many cases where the fast readout was not being used. So if we did use fast readout, if we could change the topology such that fast readout will be used in all cases, then these numbers will go up to some extent. But still, the good news is that it's probably not go up from 4% to 50%. It probably be something in the 10% range, which is what probably is acceptable. Because my guess is that most service providers would not take the fact that if we say that IP fast readout, or for that matter, MPLS fast readout takes 50% more capacity, which it doesn't. Now, another thing that we can do is that since we can have QoS in the network, we may not even need to protect the whole bandwidth during this IP fast readout. And this happens only for a short time, maybe a few seconds or maybe even 500 milliseconds or so, all right? So for that period of time, we could make the network design to have something, say, 110% utilization, which means that at least 10% of the traffic will be dropped on the floor, but that will be the bottom 10%. Only the best effort traffic will be dropped if we have QoS in the network. Those are the ones which are probably not even looking for fast readout. The ones that are looking for fast readout is probably the top 20, 30, maybe 50% of the traffic, and they will still be prevented by this mechanism. But the beauty of that is that we can get that. Like if you look at the last column and the second column, the difference is very little. We can get IP fast readout almost for free. Again, it may not be true for all topologies under all conditions, but at least in one example we show here, looks pretty, I guess, convincing. Okay. All right, actually this is my last slide, so I think I'm being on time. The main ideas we have here is that if we do, fast readout, then the simple scheme to use would be loop-free alternate. It doesn't really depend on your neighbor to do anything special. And only drawback is that there are maybe many topologies where its coverage may not be high enough, like at least as high as we would desire. If we add more complexity, like U-turn alternate, or for that matter, any of the other algorithms, then coverage can be made very high, maybe close to 100%. But still, one difficulty is that if we have to have router avoiding alternate paths, then it will be more difficult to achieve the same level of coverage. Now, also it is possible to have the IP fast readout in the backbone, and we can get some of the benefits. We don't necessarily have to use it on the whole network, but of course if we can do it edge to edge, then benefits is even better. And the final point is that the extra capacity needs of IP fast readout was not very high, at least in one example, which means that it will be Oh, I'm sorry. Okay. Okay. All right, now I'm not pointing at you. But anyway, I don't even need to point anymore. I'm all done. Okay. All right, so that's about it. And if there are any questions, I'd be happy to take that.
Okay, we have a question here.
Okay.
Hi, Virendra here. Yeah. I'm interested in knowing, say, if my network, if it's a large connected network, and if my network is converging after maybe a congestion collapse or so,
right.
And if I was doing a packet tagging for my mission critical or delay sensitive application,
right.
During the event of convergence and my application being tagged in an event of congestion, how would the reconvergence work? I mean, would it have a higher precedence?
Okay, so are you saying that if we do IP fast reroute, then our normal IGP convergence may slow down? Is that the
right?
idea?
I'm saying how would that work with packet tagging, while my application is trying to use the link in an event of congestion, because what I'm doing is I'm assigning priority to my mission critical application,
right?
And my network is trying to converge, just recovering from maybe a congestion collapse or so. During the process of convergence and my application, which has a higher packet tagging, and it's trying to go over the link, how would the convergence work with...
but you're still talking about IP network, not MPLS, right?
Right, that's correct.
Okay.
So not all of your traffic needs the IP fast reroute, the better convergence time, right? The rest of it, you are willing to do what it does today, which is best effort, which is it waits for the network to finish, waits for the convergence to happen. You drop it for, depending, 50 milliseconds, a couple seconds, whatever, depending upon local and network. So that if you have the utilization of the links be allowed to be higher, as Gagan was suggesting, during the convergence time, that means, well, more of your best effort traffic is likely to get dropped, right? And the mission critical, as long as it was, within the necessary bounds, would get the benefit from the fast reroute.
Right.
Okay.
Does that answer your question, or?
Kind of. We can take this offline.
Okay, sure.
Thanks.
Okay.
Okay, well, I'd like to thank our three panelists for their description of this analysis ongoing research.